All right, I want to thank everyone for joining us today for High Performance Computing for MIDAS members. So the purpose of today's webinar is for MIDAS members to be introduced to the high performance computing options that are available to our member group, specifically the MIDAS high performance computer that we set up at the MIDAS Coordination Center, but also the offerings from the COVID-19 High Performance Computing Consortium. So these are things that as MIDAS members, you're welcome to, and we want to give an overview of these available tools. So our guest speakers, I'm Jeremy Espino, and I'm joined by Kim Wong at the MIDAS Coordination Center. We manage the high performance computing and technical infrastructure for the MIDAS Coordination Center. And guest speakers today, we have Sean Brown. He's director of the Pittsburgh Supercomputing Center, and he's also a member of the COVID-19 High Performance Computing Consortium. I don't see Michael Martin from the collab, but maybe he'll join us in a bit. There he is. And then we also have Dave Galloway from University of Pittsburgh Public Health Dynamics Lab, FRED project. So the agenda today, I'm giving the introduction right now. Everyone will get pretty much about 5 minutes per section. We'll have a description of the MIDAS HPC machine. Kim will do that. And then we'll talk about how to apply for a MIDAS HPC allocation, and I and Kim will do that. And then Sean will talk about the High Performance Computing Consortium, how to apply for that. It's specific for COVID-19. This is in addition to the Exceed platform, specific for COVID-19, and he'll talk about the benefits of applying for that. We'll give the opportunity for two existing MIDAS members to talk about their experience using MIDAS HPC at the MIDAS Coordination Center and applying for consortium allocations. Finally, we'll give a demonstration of using our machine at the MIDAS Coordination Center, just to give you an idea of what that's like. If you're used to using a high performance computer, you'll be right at home. You can see it's just like any other high performance computer that's set up these days, and Kim will handle most of that. And then we have 20 minutes allocated for questions, plenty of time for questions for our attendees to talk about not only the machine, but how to apply. So you can ask our panelists about that. So briefly, the machine at the MIDAS Coordination Center is a on-demand high-performance computing machine. So we set this up on the Google Cloud, and we also have plans for AWS. Specifically, we set this up as an on-demand machine, so it's cost-effective for the NIH and also high-performant. So when it's idle, it only uses 2 virtual machines. And as resources are requested, compute nodes are requested, they spin up. And you'll see that happening as we do our demo. It also makes use of the NIH Strides program, which gives us discounts. NIH has partnered with the cloud vendors for discounts on Google Cloud, Amazon. So we're currently using Intel Skylake. The newer chips, when we set up the machine, we're just in testing. So we have plans to upgrade our partitions to Cascade Lake or the newer AMD chips, because those are in service now. The current offering in our partitions has a 32 gigabit per second bandwidth. So it's not like an OmniPath or a super high performance network suitable for MPI. So we will say it's suitable for embarrassingly parallel jobs or large shared memory jobs. We have a couple of nodes that have almost 1 terabyte of memory. Also, this is not a HIPAA sanctioned space, so no personal identifiable information should be put on this particular machine. So right now, I'll turn this over to Kim Wang, who will give us a overview of our machine at the MIDAS Coordination Center.
Okay, let me see if I can share screen. Let's see where we, yep. Okay, so thank you, Jeremy. So essentially, the MIDAS cluster is a HPC cluster, a SLURM cluster on GCP. In terms of the compute node configuration, we put it into 2 different partitions, one for large memory and one for standard regular memory. The partition names are N1 standard-32, and then there's an ultramem-40. Pretty much tracks what Google uses for their nomenclature as well. The wall time is 3 days. For the standard memory, it's 32 virtual CPUs and 120 gigabytes of RAM. For the large memory node, there's 2 of those. Those are 961 gigabytes of memory and 40 virtual CPUs. Now, if you look at this and you say, well, I want some different kind of hardware, we can also provision that as well. It's not a big deal. We make changes to the SLURM configuration, and we can add, and it will show up as another partition when you execute sinfo. And when you submit the job, you target a particular partition, and then you get the resources that you need. So if this does not satisfy what you need, just let us know, and then we can re-architect the cluster. This is one of the benefits of having our HPC environment and our compute resources in the cloud, that it's highly configurable and it's also elastic. You get charged when you use the compute side. So this is as much as I have for what we have configured right now. When I go through and demonstrate on the terminal, how you access, and then the resources that we have in terms of the software stack, you can see exactly what it looks like. If you're familiar with SLURM, this is very simple to use. When we made a decision to kind of mimic what a standard, which institution HPC center might be using, which predominantly is a SLURM type of cluster because of its open source nature. And we also use modular environments to provide the packages. Now, if these are not good for you and you prefer containers, that's perfectly fine. We have experience and we have expertise to deploy containers as well. Let us know in the application what you need. And then our job is to provide the infrastructure, provide the hardware, and also the software infrastructure. So tell us what software you need. We can install all those and we'll test them. And then when you are ready to run, if you are unfamiliar with how to make a job queue script, we can help you as well. And I guess that's all I want to say for now, Jeremy. All
right.
Yep.
Yeah. What I'd like to tell everyone is if you have questions, feel free to enter them into the chat window or QA window, and we'll discuss those questions during our QA session. I think some common questions just right now, really quickly. Do you guys have GPU nodes, Kim?
We do not, but it's simple to add them on. They are charged more expensive, so that's the only thing. One comment though. So there's funding for the HPC resources, and then to make it available to the broader community, you put a cap in terms of how much we fund. And right now it's $5,000 worth of compute credit. And so if you're using GPU nodes, those can be eaten up pretty fast. in terms of how we enforce that, there is a bank system within SLURM, and what we did in the beginning is we run a typical job over 1 hour, and then check the bill to see how much was being charged, and then use that as the basis to map it back to how many service units that we need to provide you. And then that would be equivalent to the $5,000 worth of compute credits that you get. Now, if you need more, you are welcome to come back and apply for a supplemental. And depending on what the amount of funds available, we could fund it as well. On the other hand, if you need a lot of resources, well, Sean is here and he will tell you about how to leverage the consortium.
Okay, thanks, Kim.
Yeah.
So right now I'll talk about how to apply for an allocation. So as Kim said, applying for a allocation where we are able to give up to $5,000 of compute per investigator for our MIDAS members after you apply. And on our benchmark right now for example, our N1 32 CPU partition, that's equivalent of around 86,000 CPU hours. So if you want to get an allocation on the MIDAS HPC machine, go to midasnetwork.us compute. You can fill out a request form, and I'm going to go through the individual parts of this particular application so that if you have questions at the end, we can answer them. Typically, we have a 1-week turnaround once approved. So we review the applications. We try to figure out what the needs are. So Kim and I have a discussion about what the needs are and what we're going to do in terms of a plan to meet the needs of a particular MIDAS member. And we do provide support services in the form of software installation. So we ask you, what software you're using, making a basic SLURM job. If you need some benchmarking, we can also do that so that you know how much compute you'll be using as you go along. So once you look at this request form, you'll see that it has some basic requests for administrative information. We want to know what your level of expertise in using high performance computing so that we can tailor our response to you appropriately. And this also includes, okay, what software you're using so we can pre-install them. And as I said, additional support about job submission scripts and benchmarking. Most important thing is probably the software, and then trying to figure out if you don't know how many cores you're going to need or how much CPUs you're going to need, we'll help you figure that out. And then, as Kim was saying, if there are other requirements that you need for your software or your project, we'll also try to allocate them as well. So one of the parts of the application is a short 1 to 2 page description of your project. And if you're not sure about any of these things, we're happy to have a discussion with you. If you don't have any performance benchmarks, that's okay. But if you do have them, that's very useful for us to figure out how many CPU hours you will require. And lastly, you get this NIH project. We definitely need information about your data sharing plan. So as MIDAS members expect that to the extent possible, your data sets and models are shared with the larger community. All right, so again, if you have any questions about applying for the HPC at MIDAS Coordination Center, we'll entertain those questions.
There's one question in the chat window, Jeremy, that says, do you distinguish between academic and industry MIDAS members for requesting compute time? This is from Jacob.
So it's open to MIDAS members. So if you're a MIDAS member, then it's open to you.
There's another question. Do you have experience using Dask directly with a SLURM in the middle? So my recollection of Dask is it's a Python, and I have not used it, but I think fundamentally, so there's two modes of accessing compute resources. One is through a job submission script, and you submit the script, and the script runs from top to bottom. The other mode is interactive. So you can use S1 to request an interactive node. Once you get an interactive node, you're sitting directly on the compute node, and you can do whatever you want. So in that case, you still go through SLURM, but you ask for a node and you get access to the node, and then you can interactively type on the terminal how you want to run your Python code. I hope that answers your question. If not, then feel free to reach back out again.
Yeah,
so
and
I have some experience with Dask. I mean, running it without this. I mean, running it on a resource like the one that Kim is talking about. I mean, you would have to basically Kim, you'd probably have to sequester nodes. You would have to take them out offline and then set that up specially to do it. I can understand why the question's asked, because the SLURM layer of Dask is not the most robust piece of software. But it can, I mean, once it's set up, it does take some setting up to do. But once you have it working and stuff, it works okay. I mean, basically, Dask is just a graph. It takes a chunk of data or a chunk of work and then just distributes it. It's like an orchestration layer kind of thing. So it can interface with SLURM. It can interface with Torque if you really wanted to, if anybody's ever still freaking using that. But you can also, the only way that you'd be able to do it, Kim, without SLURM would be you'd have to take things off and then set it up specifically to do that. It's great for like a one node type thing. It really works great for that. But once you start doing distributed, it becomes a little challenging.
So the one node, if you ask for interactive, then you can do what you need to do with Dask. For the distributed, the only thing is it's an auto-scaling cluster. So unless you provision the nodes already, you don't get it. And the only way it's provisioned now is through SLURM when you request a resource. But there could be, so I can take a look some more and see how it could be done. Well, I'm pretty sure someone has asked this question and someone has came up with a solution for it. And so it's a good use case. So let me do some homework on that.
okay. So I just want to make a correction to what I said earlier about in terms of HPC availability to industry users. Industry users are not eligible for the no-cost HPC. So you have to be a non-industry MIDAS member. So that's a correction. And thank you, Sean, for your experience in using Dask. So I'm going to turn it
Great.
to.
I didn't mean to make it sound like I didn't like. I like.
No.
Dask.
If you've done it before, you know how many hoops you'd have to get it going. So I'm going to turn the talk over to Sean, who'll talk about the COVID HPC consortium.
Okay, great. Can you guys see my? I just have the web page up. Does everybody see that?
Yep.
Okay, so yeah, so I'm my name's Sean Brown. I'm the director at the Pittsburgh Supercomputing Center. I go a long way back with many of these guys. I've worked with Wilbur, Dave, and Jeremy and Kim for a long time. Used to do public health simulations. One of the things that our center here at the PSC has done is joined this organization called the COVID-19 High Performance Computing Consortium. And it was an endeavor that was triggered by the White House at the beginning of the pandemic, somewhere around February, to gather together industry, academic, and government organizations to provide essentially capacity for the research community free of charge and urgently for 6 projects that roughly are around 6 months in time length to address specific projects in combating COVID-19. So it's been pretty successful. As you can see, there's the website that I'm on is, if you put COVID HPC Consortium into Google, you'll get to it. But it's like COVID-19 HPCconsortium.org. We have like 92 projects, tons of cores. This is literally a consortium of all the major supercomputing resources in the country, as well as now we've added resources in Japan and the UK. We meet weekly to go over proposals and assign time on the machines. And it also comes with help and support from all of the centers that you work with. So just to give you an idea of who's involved, you can see it's all the big names in industry, all the big corporations are there. Pretty much all the computing centers in the country are there. All the NSF's computing centers through Exceed are available. DOE labs also are available. So you can get time at places like Oak Ridge, Los Alamos. You can get time here at the PSC or pretty much at any of these locations. So the way it works is it does have to be COVID-19 related research, computational research. There's no restriction on what you're doing. We have projects that span the gamut of computational science, including genomics, sequencing, a lot of molecular dynamics and drug discovery, quantum chemistry. We've got a lot of machine learning and AI projects, as well as we have one really agent-based modeling project that's Madhav Marath out of the University of Virginia doing his agent-based models, nationwide agent-based models. So the consortium is very open to anything as long as it is directly addressing the COVID-19 pandemic. So if you go to this website, you'll see you can get a lot of information. You can see all the projects and such that are there. There's a button on the corner here called Apply, and you just click on that, and that takes you to this page, which then takes you to the Exceed portal, which gives you instructions on how to apply. Now, each of the proposals, this is a fairly lightweight proposal process. It's a 3-page proposal. Basically, the important things to put into your proposal are: why is it important to COVID? A little bit about the computations that you're doing, and then some estimation of the amount of computing resources that you need. Like I said, we have cloud resources, we have GPU resources, we have parallel GPU resources, we have normal CPU resources. We have basically there's a lot, like Open Science Grid's a part of this. Jetstream is a part of this in the Exceed. There's like even one computer called Summit, which is a large, massive GPU cluster, which may not be that interesting to all of you, but there's a very big gamut of resources. So whatever you need is there. And generally, we're trying to support people that need beyond what they have at campus or beyond what you normally can get on your workstations. You have a need for high performance computing and large amounts of resources. So basically, you would go to this website, you would sign up for an Exceed account, and then you would submit a proposal. Maximum 3 pages, like I said, really hit hard the why is this important and why will it have an immediate impact on the COVID-19 pandemic, and describe what you're going to do, the science behind what you're going to do, and then a strong estimation of the amount of resources that you will need. If you're doing AI and machine learning, we realize that that's not necessarily necessary or possible. So having some idea of like how your model performs, like the time per epoch and things like that, can be very useful in helping the reviewers understand. So each of the proposals goes, like I said, weekly. On Wednesday, we meet, the reviewers meet. There's reviewers from around the country, both COVID-19, public health experts, chemists, biologists, and people that are and computational specialists. And then on Thursday, the meeting that I go to is we match them up. So you'll be able to specify what kind of resources you want, and then you'll be matched with a particular vendor or group that will help you get started and get your resources done. So yeah, so like I said, pretty much anything. Amazon's part, all 3 cloud providers are behind this. Google, Amazon, and Azure. So if you want cloud computing, you can get that too. So it's really kind of open to, it's there to help. So if you're interested and want to apply, I urge you to go to the website, and I'm happy to help if needed. I've seen a lot of these proposals. I was a part of this from the beginning, meeting 3 times a week to review these proposals. So let me know, and if you need it, it's there, and we're still awarding time, and there's still plenty of resources to be had. So yeah, I just want to let you guys all know about that, and it's there and available for you if you need it.
Thanks, Sean. So I want to make sure that MIDAS members know that the Coordination Center is here to help you submit proposals to the High Performance COVID-19 Computing Consortium. We've done this with the CoLab, and Michael Martin and his group have done that. So in particular, crafting a proposal that is appealing to the consortium, and making sure that it will get accepted and your allocation will be placed. And so this COVID-19 HPC consortium, particularly good if you have a lot of requirements and want to use the bigger iron that is available, as Sean said, among all of the HPC machines in the country. So I'd like to turn it over at this point to Michael over at the CoLab, who's used the HPC machine that we have and also submitted a proposal to the consortium, and he can talk about his experience doing so.
All right. I'm trying to start my video, but it says the host has stopped it.
Let me see. Okay, I made you co-host, so you should be able to share now.
Cool, awesome. Okay, so I'm going to talk for a few minutes about some of the work we did utilizing the MIDAS HPC resources for SARS-CoV-2 Bayesian phylogenetics. And so, yeah, we have applied for, or in the process of applying for, a COVID-19 consortium allocation, but all of this was done on the MIDAS HPC resources. So before I go really talk about how we use it, I just wanted to say that all of this work was part of a project in collaboration with Katia Cole, my advisor, and Adi Stern and her graduate student Daniel Miller, who are at Tel Aviv University. And it's all published now in Nature Communications. And here's a GitHub link, which has all of the code to replicate this either on the MIDAS cluster or sort of any machine. So the goal of the work that we did was to sort of infer epidemiologic parameters of SARS-CoV-2 spread within Israel during the spring wave using sequencing data. So we did this with this suite of programs, which are all come pre-installed on the MIDAS HPC resources. So it was like very quick and easy to get up and running relatively once we had access to the resources, because it's all pre-installed. So Beast is a program which lets you sort of input your sequencing data, your viral sequencing data, and then sample evolutionary phylogenetic tree space to infer how the virus is evolving. And you can run it, and it relies on this Beagle library, which just improves the speed, but I'm pretty sure it's pre-set up on the MIDAS HPC resources, so it was very easy to use. And then these two bottom packages that we used are Beast packages that are also pre-installed. So this one on the bottom left, Fidine, is developed by Eric Voltz and Igor Civaroni, and it allows you to sort of fit compartmental models using your sequencing data. And then on the right, this is a package that I used, which basically allows you to run multiple MCMC chains at a single time and swap between those. And it can help you get out of bad spaces or bad areas of likelihood space. So one thing that I do want to say about this, because it's something I didn't fully realize, I guess, is it essentially triples the computational cost of your job or doesn't, depending on how many chains you run. So I was running 3, so it tripled it. So it's just something to keep in mind in terms of like how much allocation you're using, because I ran through a lot of allocation very fast because I wasn't aware of that. Okay, so like I said, many packages, many of these, or all of these weren't pre-installed. And so you can sort of see the list of different Beast packages once you load the Beast module on the MIDAS HPC by running package manager list. So this is, I did this yesterday on the MIDAS resources. So there's a lot installed. It's great. Okay, so this is sort of just the data that we used was deep sequencing data from, or not deep sequencing, sequencing data from Israel and also outside of Israel. And sort of the way Beast works is you have to give it a Beast XML file that defines things like your evolutionary substitution model, and then also how you change parameters at each MCMC step. And those are called operators. So the best way to do this that I've found is there's a program called Beauty, which comes along with Beast, and it's a GUI, and it lets you sort of set up an XML file. And I like to set up sort of a template doing that and then modify it by hand. So on the GitHub link that I had at the beginning, there's I have sort of the templates I use, and I find that to be really useful instead of just going back to Beauty, because it can be a little hard to, I don't know, I don't find the GUI the most intuitive. Okay, I will skip a little bit in the interest of time. So this is the SLURM submission script that or an example SLURM submission script that I used. So as I mentioned, I was using that parallel MCMC approach. So that's why I request 3 tasks per node. These jobs are pretty memory low intensity. So we just do the standard partition. And then I was trying to run these for 10 million time steps. So I requested 3 days of runtime. I don't think any of them quite went that long, but they were close. And then these are the modules. This job, it's fairly simple submission script, but these are the 3 modules you have to use load. So Beast 2, and then the GCC compiler, and then Beagle, which is that library. And then this is the actual Beast command. So you just request 3 threads for the 3 parallel chains. This prefix flag just determines where your output files go. Overwrite to overwrite any existing output files. And this is the path to the XML file I was using for this example run. And I just wanted to say sort of, I guess I'm almost out of time, but we ran this, we've also, before we had access to the MIDAS resources, we were running this on another system, and to get sort of 10 million MCMC steps for basically the exact same model, it was taking about 8 hours per million steps. Whereas on these MIDAS resources, it cut it almost in half down to like 5 hours. So that was really accelerated the rate at which we could run these and get results. So that was really great. And you could probably optimize it more. I'm not an expert in sort of the computational or sort of the optimization side of things, but getting it down to 5 hours per million MCMC step compared to 8 was really massive. So that was great. Okay, I will stop there.
Thanks.
But yeah, I have my email at the beginning in case anyone has questions about using Beast on the cluster. It's pretty easy to set up, but I'd be happy to help anybody.
Thanks, Michael.
Yeah.
And as Michael was saying, their group used quite a amount of compute, and they applied for a supplement, and we granted it to them so they could further do their project. And then just to follow up on their lab and their need for additional compute, they applied to the COVID-19 consortium, and hopefully they'll get their compute on there and have lots of hours to use on that machine. So I'd like to turn it to David Galloway over at the Public Health Dynamics Lab, talk about his use of HPC.
Hopefully I can share this.
Yep, we got it.
And all right, so I don't have any results or anything to show. I just wanted to talk about the what we were using it for. I think a lot of people on this call actually know about FRED, but I do have the typical FRED, what it is and what we are. We have an agent-based modeling framework. The important thing is that every person in a geographic region is simulated. And so it was originally developed for infectious disease, but over the years, particularly since back when Sean was working on it, it's been extended quite a bit to look at other things, including various health conditions. But for this particular thing, we were back doing infectious disease. So that was interesting. The challenge with FRED, and again, Sean would know this stuff better than anybody, it's memory capped. And because every simulated person in a particular location is in memory, they have to be in the RAM at the same time. So if you're running a small, running a simulation in a small county in Pennsylvania that only has 50,000 people, you don't need that much RAM. But if you want to run the entire state of Pennsylvania, you're looking at I think 8 million people. The RAM needs become very high, and because it's a stochastic simulation, basically whoever is the first person infected has a big determination on the outcome of what's going to happen, particularly in something that's very an infectious disease like this. If the original people that we infect are, hermits, they may never infect anybody. So because of the stochasticity, we need to be able to run the simulation multiple times, 50, 100 times, just to get some sort of good means and standard deviations. And the runtime is affected by a lot of these options. So how many agents we're running, whether or not we want to be able to visualize the results, that adds a lot of files, a lot of file writes, a lot of overhead. And we have another option to output health records, which is basically like every state change that happens in the model gets written to a record file. That file can become very large, and it's a lot of writing. So if we're doing that, it adds a lot to the runtime. There were basically two simulations that we looked at quite a bit. This was back at the early part of the COVID wave. This first one looks at social distance compliance. And so we were trying to match COVID deaths that were reported. Now, again, reporting early on was not great, but we needed something to be able to calibrate to. And so we made some assumptions on these initial runs that, we were going to do it on Pennsylvania. We had information particularly on Philadelphia and Pittsburgh, and we really didn't know what the R naught of the simulation was. And but we just used at that point, we used 2.0. We assumed the start of the infection was March 1st. We just did 100 people were picked at random. And we assumed back then, I think that March 15th was when schools closed. And March 21st was like when Pennsylvania went on this lockdown. And so those were like assumptions that we did for our runs. And what we were looking at was what would happen if we changed the compliance and we wanted to do multiple scenarios, going from absolutely no compliance all the way up to 100% compliance, just to see if we could get something resembling the deaths that were reported. And again, reporting of this was not great at that time. The other type of scenarios we were doing had to do where we were trying to match those numbers. But at this point, we said, all right, we're going to assume the compliance is 60%. But we're not quite sure about the R naught. And what if the infections began earlier as opposed to, I forget what I said on the original one, but I think on the original one I said March 1st. What if it actually had come to the United States or come to Pennsylvania sooner? Could we match the numbers that we were trying to get to? And as I said in the original challenges, FRED has no like parallelism. There's no multi-threading or anything like that. It is entirely, how much you can get in RAM. And so if we want to run, the more we can run at a time, the faster we can finish the simulation, but we need a lot of RAM to be able to do that. So, if we're looking at small counties in Pennsylvania, we probably can do that in the smaller node. But for to be able to run multiple realizations of, say, the entire state of Pennsylvania or New York City or Chicago, if we were looking at those ones, we actually needed at that point to use the large memory nodes. And it's not because it's because we're trying to run as many as possible at the same time, and we're limited by the number of cores, of course. I have in here these scripts that I wrote, but nobody wants to read code. The bottom line of what I did, all these did was they just created a bunch of SLURM scripts. But one of the things that our job script does, and you see here, it says Fred SLURM job. That's a Perl script that we wrote that does the actual like running a Fred, compiling all the data, whatnot. But the problem was that it was originally built for a whole bunch of sequential runs on a single system. One of the things that Kim was immensely helpful on was figuring out how to be able to submit Fred specifically to the nodes directly, which is what I want to be able to do. So I have here how I get the node list. And so this scontrol show host name, that actually pulls back the nodes that were allocated for me during the run. And then the other big thing that Kim helped me with enormously was being able then to submit each particular Fred job to a node directly, which what he showed me how to do was to execute the SSH password list. So I had to go into each one of the nodes and set up so that I could do the passwordless login. But by doing that, I was able to connect all of them, all the nodes that I needed at once. Now, again, this isn't for the large memory node. This was for running, say, Allegheny County, 25 times. If I had 25 nodes, I want to run each of those, connect directly to each of those. And so that was what this was, the SSH being able to connect directly to the nodes. I think that's all I have was those created the SLURM scripts that I needed. But that's it.
Great, Dave.
And how do I give it back to you? Stop
you.
share. I see. All right.
There you go. So this is an example of two of our members who were using our machine. David, have you also used for example, the PSC machine before?
I've used the PSC machine. I also use the PIT CRC machines, and
Right.
it's similar, but not exactly the same for each of them. But honestly, I should go into our job script that we, our Fred job script that we have, and utilize srun so that I can not have to do it this way. But John Greffenstedt wrote this a long time ago to get all of the data together, and I'd need to go in and figure out how to pull from each of those nodes and make sure that each of them gets, each srun gets a unique random number key. Otherwise, they'll all run the exact same 10 runs or whatever. So so it was something that I would like to mess around with at some point. But back when this was going on, I was kind of in a rush and being asked, hey, I need this information now. And so I just modified John's script the best I could.
All right. So again, if you guys have specific needs with regards to your project and what you're running, we can help craft the infrastructure and workflow in a way that makes sense given the resources that you're going to need. So I'm going to turn the discussion to Kim, who will give us a demonstration of using the machine.
Okay, well, let me see if I can share this. Maybe this one. Okay, you should just see a terminal. Cheese grater. Is it? Okay. All right, so this is more kind of a demo about how you access the HPC cluster. Well, at the moment, there is only one mode of access, which is through the terminal. So for people who are heavy on Linux, they say, oh, this is great. But for others, there might be a barrier for learning. But the barrier is small, so we can help you. So let me start from here. So this is on my home machine right now, and let me do this. So I made an alias so that when I ask this, so this is the command to log into the cluster. My MIDAS username, and then this is the cluster right here. So I made an alias for it, so it's easier to just type MCC to, and then bam, there I am. I'm on the cluster. All right, and it's a SLURM cluster. Let me let me get rid of this conda stuff to make it easier. All right, so it's clear. So what resources do we have? So SLURM has a sinfo. That's the SLURM command. So it tells you what information there is about the partitions. So this is exactly the partitions that we have: a regular memory and then a large memory, and then the 3-day wall clock, the number of nodes that we have configured for the cluster. So you can ask up to 72 nodes on the standard 32 core B processor partition. Okay, and then the host name for the nodes are this, and then it's 000 to 71 essentially. And then the same thing for the large memory, which is around 961 gigabytes. And so for 0 to, and then 1. So that's it. So that's what we have in terms of the resources. Now, thank you, Michael, for presenting your SLURM script, because it's really instructive. The way that we provision software is a module environment. So module avail will tell you what we have installed. And essentially, what have we installed? What we have installed is what our users have requested. Okay, so the basic compilers, and then some users that I need Python, I need R, or I need MATLAB, and then here's Beast and Beast 2. So all of this, and then within Python itself, we install libraries that you need if you so desire. You can also do it locally on your own home directory. Whatever your preference is, just let us know. If we can help with doing it globally, we can do that as well. Same thing with R. So this is what we have so far in terms of the software stack, and we can grow it as the demand increases. Now,
can you show the spider, Kim, so they see the whole thing, the whole list?
Yes. Okay. So module spider. I guess this is just, so this all, there's a lot more actually. Yeah. But module avail, and this is all shown in our documentation that Jeremy wrote up, and it's a nice documentation. So if I do module, there's a module spider, and then a particular package. If there's dependency, it will tell you. So this one does not. So you can just do module load beast, and it will load beast. So why don't I just do that? Module load beast. And then module list shows you, okay, what's loaded is beast, and these are standard, LMOD and the bank. I'll show you the bank in a little bit. Now, there are packages that have dependencies. So let me take a look at, module, is there an MPI? I don't remember. Yeah, there's MPI, module spider, open MPI. Yeah, module spider, and then I give a particular version of MPI. And it will say, yeah, this version requires this particular version of GCC. So if I do module purge, which removes everything, so there's no modules loaded, and I do module load, the OpenMPI 4, it will say you can't do it because there's dependencies. All right, and so it's the module spider OpenMPI, and it says, well, you can load it, but you need to load the GCC compiler first. And I'll try to explain why that is the case. So if I load GCC and then OpenMPI, there's no complaint. So if I list what I have loaded, it says I have GCC and OpenMPI. So why are there dependencies? Because it's a shared environment, different packages have different dependencies, and it can be that they depend on a particular version of a compiler. So what the modular environments allow us to do is build in, and it's LMOD. What it allow us to do is build in this logic where if you try to load a package that has dependencies, you will be alerted to it, and it will tell you, yeah, you need to load these first, and then when you load the dependencies, then you can load the package that you need. So so this makes the environment usable to a broader field, broader area. Okay. Let's see. What else, Jeremy? You have anything else? I'm going to show. So SQ says what jobs are in the queue. Okay. So Michael. Okay. So the associate group CPU min limits, it means that they're out of service units. They used up their allocation. So let me take a look. So S bank balance statement dash A. Oh, I'm sorry. I want to load S bank. Does it work? Oh, let's see. It's not S bank. It's a SLURM bank. Okay. Well, great. I thought I was going crazy. So this. Okay. So this is the banking, and basically available CPU hours in pretty much, I think Jeremy said, for about $5,000, it's roughly about 85,000 CPU hours. And then this tells you how much is left. And I guess Michael, yeah, you guys are out of SUs. So now I think we helped Michael and the lab to target the consortium HPC resources, and then okay, I'll eat later. Okay. Okay, just wait. And then, so basically what this says is, we can help you and provide you resources to get started. And because there's funding for these specific resources, if you need more, you can ask for a supplemental. But beyond that, if it's substantial resources to push the next envelope that you're trying to do for your research, NIH funded research, we can help you go to the national lab and get resources from national lab or national supercomputing centers or the COVID consortium, HPC consortium. Okay.
Can you submit a job, a quick job, and then we're going to save the last minutes for questions?
Yeah. So, okay. So let me clear this and do sinfo. So sinfo says, actually right now everything's idle. So let me submit a interactive job. So srun dash nodes equal 1. Oh, let me back up. Sinfo. So srun dash nodes equals 1, and then dash partition equal, and let me, I'm going to copy. So this is the partition. Okay, and then time equals 1 hour. Let's just do that. And then pty bash. So S1 is a SLURM command. So it's waiting for resources, but let me show you. Right now, everything is idle. But if I query sinfo again, what it's saying is, originally, there were 72 idle nodes, okay? But there's a job that's pending, and it's asking for a one compute node, and it's this job that I submitted. The compute node is not ready because it's a auto-scaling cluster. It's in the idle state, you don't get charged, all right? And so now it's trying to find the resources that you've specified, and then it will spin it up. So it takes about maybe a minute or so.
It's about a minute, yeah.
Yeah.
And if you're submitting multiple jobs serially, the compute nodes that are spun up, they have a idle lifetime of about 10 minutes. So if you continue submitting jobs, there will be no spin up time. So it will just immediately run what you've submitted, basically.
I hope it, well, there's no error. So it should, what this means is the queuing system. Oh, okay, that's great. Okay, so you notice that the host name originally was the login node, so the HPC login, and now you have a compute node, and it's the first one that was configured. So I'm on a compute node right now, and so interactively, if I have a Python script, I can do Python and then my Python, the Py script, whatever you have, right? So you can do whatever you want when you are on the compute node, and the compute node has the processors, the beefy processors that will do the compute for you, as opposed to the login node, which is very lightweight. Now, if I go back and take a look here with sinfo, and I query sinfo again, you will see that 71, and then you'll have one that's already allocated. Okay, so it's running, and this is the node that was allocated, which is the job, here. Now, back to what Jeremy said. If I get out of this, so I'm going to exit out. So I'm kicked back to my login node, and if I query again, let's see, what does it say? It says it's, so instead of it's allocated, meaning you're being charged and it's allocated, it's now in the idle state, but without the tilde. The idle with the tilde means it's configured to provide those type of resources, but it's not, the node is not available yet, but we have to spin it up. In the idle state, it means you're still being charged, but there's no jobs running on. Now, if I go back and ask for a compute node again, it should just kick me in immediately, because it hasn't spun down yet. It's still in the idle state. So if I do sinfo, you're allocated the compute node. So the timeout is what, 10, did you say 10 minutes?
10 minutes for an idle node that has no jobs running on it.
Okay, so basically what that means is if you, so one scenario is you have a script and you want to, and it's finished, and you want to run a different script, you can go back onto the same compute node and execute what you need. Let's see, what else, Jeremy?
I think that's good. It certainly gives an idea how you can run in an interactive session.
Yeah.
And most people, if you have a tremendous amount of runs, let's say you want to do a parameter sweep over one of your algorithms, then you'd be in the area where you want to do a batch submission. And this is what Kim is showing now, where you set up a script that you can run with, let's say, many different parameters and execute it over multiple nodes. And that's a way to get your results, a whole slew of results in very quickly, because they'll be running over multiple nodes.
Yeah.
But certainly the interactive way is available as way.
Michael touched on the job submission script. Essentially, I break it down into 3 parts. These are called SLURM directives, and this is similar to what I put on the command line for the interactive. You just specify the resources that you need. And then there's the provisioning the software stack. Okay, so I want R, and the R depends on all these. And then the domain-specific execution line that you would otherwise do if you're on the command line. So that's it, and then bam, you're good to go. So let me go to one example of a multi-node, and then I'll turn it back to you, Jeremy. So so by training, I'm chemical physics, so I know a lot of math and I know a lot of compute. And so molecular dynamics is Amber. So Amber is molecular dynamics. And what this says is I'm going to run a Amber job. Here is the standard execution line for Amber. And to make the software available, I'm going to load Amber 18. Okay. And then I want 8 compute nodes, and each of the nodes, I want 32 processors. And so now it's an MPI job, so 8 times 32 number of processors working on this Amber job that you have to find in your input files. And it's a molecular dynamics code. So that is multi-node, although the networking between the nodes is not optimal, but you can do it. So that's the bottom line. I'll turn it back to you, Jeremy.
Okay. Thanks, Kim.
Yeah.
So as you can see, you can automate things using scripts, as David and Michael had done. You can run interactively if you want to run on a node with a lot of resources and try a bunch of things out, like doing some Python scripting and seeing how it works out on the nodes that you'll be using. So one of the questions I have here is, I'm not familiar with HPC. Is there a way to get hands-on experience in order to get familiar with it? So we're planning on a more in-depth webinar on hands-on HPC and using SLURM, allowing users to practice basically on creating job submission scripts and understanding them. I also want to point everyone to Exceed and the Pittsburgh Supercomputing Center. They have really, really good instructors in terms of how to use SLURM, which is the job manager, which we all use for high performance computing, the most popular one, how to write scripts, how to submit scripts, and how to accomplish some of these workflows. And all of these particular scripts and workflows are really, unless it's really simple, and so a lot of people do have very simple workflows, on tuning it and making sure that you're using the resources effectively. So we'll be doing that at a later webinar. And another question we have is explain the differences of any between the COVID HPC consortium and the MIDAS application. So these are two separate applications. The MIDAS HPC application is for our MIDAS Coordination Center machine. It's a smaller machine with 74 nodes. And the COVID-19 HPC consortium is specific for COVID-19. So if you're doing a COVID-19 project, and makes available any of the high performance computers in that particular network. And that includes groups, the Exceed group, I think Lanel's on it, I think, and then Google, Amazon. So making the full breadth of high performance computing machines available to people who are doing work in COVID-19. So that's particularly important if you have a lot of compute requirements and you want to get on there for your COVID-19 research. Let's see, any other questions here? So if you have any other further questions, I posted in the chat window our email addresses. Feel free to ask any questions about the machines or applying. Sean's available for the COVID-19 HPC consortium. If you've got your research and you need compute, you should definitely apply for these resources. We can help you at the MIDAS Coordination Center apply, write up your proposals and things like that. And I want to thank our guest speakers, David and Michael and Sean for joining us, making yourself available. Again, any questions, feel free to ask. The Coordination Center is here to help you get your research done and find out the questions that answer the questions that you may have. All right. With that, we'll end the webinar. Again, thanks everyone, and have a good weekend.
Thank you. Take care.